Okay, hello everyone. Today we are going to learn second course of the probability, and it would be very fun. Section 2.5 is calculating probability of event, the sample point method. So to calculate probability of event, there are two type of methods. The first one is the sample point method, and the other is the event composition method. We are going to learn the event composition method in probably about chapter 2.9. So for now, we will uh, just talk about the sample point method, and it's about assigning how can we assigning probabilities in each simple event, and let me describe how we do. The following steps are used to find probability of event by using the sample point method. Okay, so step 1, we define the experiment and determine how to describe one simple event. So given the situation, we first define the experiment and then determine how to describe one simple event. And the second, we list all the simple events associated with the experiment. And this step defines the sample space S. So when you are listing all the simple events associated to the experiment, that's describing your sample space S. Okay, and the third, we assign probabilities to sample points in S, which is for all the sample for all the simple events EI, we assign probability that have greater than or equal to 0, and also the sum of all probability of simple events would be equal to 1. We assign probabilities this way. And the fourth, we define the event of interest A as a specific collection of sample points. So this is the set that we are interested in the problem of the probability. We will see the example in the next slide. A sample point is in A if A occurs when the sample point occurs. Test all sample points in S to identify those in A. Yeah, this is how we define the set A, the interest set A. And next, the find probability of A by summing the probabilities of the sample point in A. And yeah, next step is calculating probability of A by summing all the probabilities of the simple event. So in the set A, there are multiple number of sample points, and since we assigned probabilities for each simple event, by summing up those numbers, we can get the probability of A. Okay, let's learn the sample point method from this example. Example 2.2. Consider the problem of selecting 2 applicants for a job out of a group of 5. Okay, so we are selecting 2 applicants from 5 people, and imagine that the applicants vary in competence, 1 being the best, 2 second best, and so on for 3, 4, and 5. These ratings are, of course, unknown to the employer. Define 2 events A and B as follows. So there's rankings for the applicant, and that's unknown to the employer, and we are randomly selecting 2 among those 5 people. Event A is the employer selects the best and one of the 2 pleased applicants. It's selecting applicants 1 and 4 or selecting applicants 1 and 5. Okay, and what's event B? Event B the employer selects at least one of the two best. Okay, so it will select at least one of two best, one of first applicant or second applicant. Okay, and the problem is find the probabilities of these events. We want to find the probability of event A and event B. And let's try the sample point method here. The step 1, define the experiment and determine how to describe one simple event. Okay, so what's the experiment here? Experiment here is randomly selecting two applicants among 5 people. Okay, that's our experiment. And let's define one simple event. One simple event is selecting applicants 1 and 2. That would be one simple event. And in step 2, we want to list all the simple events. We want to list all the simple events associated with the experiment so that we can define the sample space S. Okay, so we define all the possible cases. We list all simple events. So E1 is selecting applicants 1 and 2. E2 would be selecting applicants 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and 5, 3 and 4, 3 and 5, and 4 and 5. And if you count, it's 10. And by this way you can list all the simple events, and this make your sample space S. Okay, now your simple events are like these, E1 to E10. And let's go to step 3. Step 3, assign probabilities to sample points in S. And here we want to assign probabilities like this. Probability of EI, probability of any simple event is greater than 0 and greater or equal to 0. And also summing up all those probabilities would be equal to 1. And in here, actually, the all simple events are equally likely. I mean, we are randomly selecting 2 among 5, and the all events are equally likely. So we are assigning the equal probability for all the cases. And since we have 10 simple events, we can assign 1/10 to each of the simple events. So we are assigning our probability of our simple event as 1/10, and that will meet this property. Each probability of simple event is greater than or equal to 0, and also summing up all the simple events, summing up all the probability of E1 to E10, that's 10 times to 1/10, that is equal to 1. Okay, so it's done. And in step 4, define the event of interest as a specific collection of sample points. Define the event of interest. Previously, we defined A and B, so we can list items included in those events. For event A, it is the first applicant and fourth applicant, that's E3, and first applicant and fifth applicant, that's E4, and that's our event A. And for event B, it's including at least one of two best applicants. So it should contain 1 or 2, at least one member of selected applicants would be 1 or 2. So this is these are the event B. So B is E1 to E7. This is our event of interest, and find probability of A by summing the probabilities of the sample point in A. Okay, so for probability of A, since we have two simple events and each um, assigned probability of each simple event is 1 over 10, so it's 2 over 10 for A. And what about probability of B? It's 7 over 10. Let's move on to example 2.3, and let's use the sample point method again. A balanced coin is tossed 3 times. Calculate the probability that exactly 2 of the 3 tosses result in heads. Okay, so we are tossing balanced coin 3 times, and we want to calculate the probability that exactly 2 of the 3 tosses result in heads. Okay, step 1, define the experiment and determine how to describe one simple event. What would be the experiment here? So here, if the experiment is tossing balanced coin 3 times, and let's denote H for head and T for tail. And let's describe one simple event. One simple event would be tossing HTH. So the we tossed coin 3 times, and 2 of them are heads and 1 of them are tail. Okay, and step 2, list the simple events associated with the experiment. This will define our sample space S. So let's list all the simple events. So event 1 would be we are getting all heads, 2 heads and 1 tail, 1 head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. So we have all 8 cases for here. In step 3, we want to assign probabilities to sample points in S, so that probability of each simple event is greater than or equal to 0, and summing up all the probabilities is equal to 1. To do that, actually here, all the events are equally likely. So since we have all 8 events, we can assign our probability as 1 over 8. Okay, and in step 4, define the event of interest as a specific collection of sample points. Okay, what's the event of our interest? The probability that exactly 2 of the 3 tosses result in head. Exactly 2 heads, that's the event of our interest. So it's let's count which event have 2 heads. E2 have 2 heads, E3 have 2 heads, and E5 have 2 heads. So our event A include E2, E3, and E5. And in step 5, find probability A by summing up the probabilities of the sample point in A. So the probability of each simple event is 1 over 8, and we have 3 of them, so it's 3 over 8. Okay, let's move on to 2.4, example 2.4. The odds are 2 to 1 that when A and B play tennis, A win. So the possibility of A winning have 2 times of more chance than B. Suppose that A and B play 2 matches. What is the probability that A wins at least 1 match? Okay, the step 1, define the experiment and determine how to describe one simple event. So what's the experiment here? A and B played 2 times of tennis and then win or lose. Okay, that's our experiment. A and B play 2 matches and W indicate A win and L indicate A lose. So, and let's describe one simple event. A simple event would be WW, A win 2 times in a row. That would be one simple event. And in step 2, we want to list all the simple events associated with the experiment. And this will define our sample space S for this problem. Okay, so simple events are A win 2 times, A win and lose second time, and A lose and win next game, and A lose lose. That's our simple event, and it will make our sample space S. In step 3, we assign probabilities to sample point in S. And actually, in this time, all the events are not equally likely. The probability of A winning is different. Actually, it's 2/3. Probability of W A winning is 2/3, and so we can calculate the probability of each simple event um, uh, by this way. So probability of E1, A win 2 times, it's 2/3 times 2/3, which is 4/9. And the probability of A win the first game and A lose second game, it's 2/3 times 1/3, and which is 2/9. And probability of E3 is again 2/9. And probability of E4, A lose 2 times, it's 1/9. Okay, and by summing up all these numbers, it's 1. So our assigned probability is okay. And in step 4, define the event of interest as a specific collection of sample points. What's the event that we are interested in? What is the probability that A wins at least one match? Okay, what the event that A win at least one match? It's E2 or E3. So the event A, it contains E2 and E3. And in step 5, find probability of A by summing the probabilities of the sample points in A. And signed probability for E2 is 2/9, and for E3 it's 2/9 again. So by summing up those two numbers, it results in 4/9. So we have 4/9 here. So far, we have learned how to calculate probability of event, and for the homeworks, actually, it's not all the odds problems, and actually, I figured out that there are probably exercise problems are a lot, so I just select 5 among them. Okay. Next chapter is about tools for counting sample points. Actually, when we are counting very large number of samples one by one, which is impossible. So it's impossible to count all the coins in the figure. So in this chapter, we are going to learn some combinatorics methods to count events in the given situation, which including permutations or combinations. They are called Sunyer and Johab in Korean. So that kind of techniques will be covered in this chapter. With m elements, A1 to AM, and n elements, b1 to bn, it is possible to form m times n pairs containing one element from each group. How is it so? Actually, the solution is just simply making a graph here, b1 to bn, and the x-axis a1 to am, and the each cell contains the pair of I and bj. Here a1 b1, a2 b2, a3 b1, and for all the pairs of m element and n element, it's m times n. Okay, let's look at example 2.5. An experiment involves tossing a pair of dice and observing the number of numbers on the upper faces. Find the number of sample points in S, the sample space for the experiment. Okay, so what's the experiment here? The experiment here is rolling dice 2 times, and we are observing upper face. And each dice have 6 outcomes, 1 to 6, and so the one simple event would be having 1 and 5. And to list all the events, to list all the simple events, we can apply the method that we have learned previously, which is we have 6 events for here and we have 6 events for here, and all the possible simple events would be 6 times 6, which is 36. Move on to example 2.6. Refer to the coin tossing experiment in example 2.3. So example 2.3 is tossing balanced coin 3 times, and coin have head or tail, H for head and T for tail. That's our example 2.3, and we found for this example that the total number of sample points was 8. Use the extension of the MN rule to confirm this result. Okay, let's extend the MN rule and to calculate the sample point of example 2.3 is 8. A simple event for example 2.3 would be this thing, head, tail, head. And actually we can describe it as like this. And here, for the inner pair, actually we can apply MN rule to count all the events for the first place. H, for this position, we have 2 possibilities, and the second position, we have 2 possibilities. So 2 times 2, by applying MN rule, the all possible event is 4. So there's 4 possible numbers for the first position here, and there's 2 possibilities for this position. So 4 possible possibilities for here and 2 possibilities for here. So all the event is 4 times 2, which is 8. So we calculated the result is 8, and actually we can extend the result using more generally. So let the number of each element for the position as m and p. So if there are m number of events for the let's say, oh, where is it? Okay, there are 3 positions, and let's say m number of events are in the first position, and there's n number of events here and p number of events here, and the total number of events for first 2 positions, the total number of events for the first two positions is by using MN rule, it's MN. And we can also apply MN rule in the next thing. So um, let the first two position as combined position. This is combined position, and the total number events for combined position and the third position. The all the items for the first position is MN, and the all the numbers for the third position is P. So Mn times P, which is MNP. So this is extension of the Mn rule. Okay, let's move on to example 2.7. Consider an experiment that consists of recording the birthday for each of 20 randomly selected persons. Okay, and ignore leap years, and assuming that there are only 365 possible distinct birthdays, find the number of points in the sample space S for this experiment. Okay, let's find the number of points in the sample space. Before doing that, let's describe our experiment, which is um, oh experiment is randomly selecting 20 persons' birthday, and one simple event would be like this: the day 1 to day 20. This would be one simple event. And what would be the total event? And for the total event, for the first position, there are 365 possibilities, and for the second position, there are 365 possibilities, and so on. So it's 365 to 20th. So these are a total number of points in our sample space. If we assume that each of the possible sets of birthdays is equiprobable, what is the probability that each person in the 20 has a different birthdays? So this is the event that we are interested in. We want to the event is that we want to have 20 different birthdays in our set. So how can we calculate that? And actually it's uh, the number of ways of ordering 20 days among 365. Actually that's the same thing. And actually uh, the number of ways of ordering 20 days among 365, if you have learned about the probability, um, uh, you maybe know, but if you don't know, like for the first day, we can pick any of 365 days, and for the second day, since you already picked one day from your first day, um, uh, you have 364 days left, because you already picked one. So there's this number of possibilities. And for the third day, since you already picked 2 days previously, the number left is 363, and so on. And so this is the probability um, uh, probability that each person in the 20 has a different birthday. And actually, this leads to the permutation part. And the permutation is the number of ways of ordering 20 days among 365, which can be described as 365p 20. Or in this book, it described like this. Unordered arrangement of R distinct objects is called a permutation. The number of ways of ordering n distinct objects taken R at a time will be designed by the symbol like this. But in the high school mathematics course, if you learned uh, high school probability in the high school, we usually describe it like this. But in this book, they describe it this way. So probably I will use both. Sometimes this or sometimes this. Probably you may be familiar with this notation better. And the NPR, this is calculated this way. And actually, the number of ways of ordering R elements among n numbers, and the proof is that for the first selection you have n choice. So for the first selection you have n number of choices, and since you already picked one from n number of choices, you have n minus 1 number of items left. So in the second place, the possibility of your choice, it's n minus 1. And what about the third position? Since you already picked two numbers from all n numbers, the possible choice for the third position, you have n minus 2 numbers, and so on. That's the proof for the permutation. And this thing can be also described as n factorial divided by n minus r factorial. Move on to example 2.8. The name of 3 employees are to be randomly drawn without replacement from a bowl containing the name of 30 employees of a small company. Okay, in the bowl, there's name of 30 employees, and you are picking randomly picking 3 employees. You are randomly picking 3 names, and the person whose name is drawn first receives $100, and the individuals whose name are drawn second and third receive $50 and $25 respectively. And how many sample points are associated with the experiment? Okay, and so the experiment here is randomly picking 3 names, and we consider order because the first guy get $100, second guy get 50, and the third guy get $25. So we are considering ordering of the event, and um, a simple event here would be a simple event would be listing 3 names like Tom, Jane, and Andy, like this. This is your simple event, and um, and we want to count the all the simple events, and that's the number of ways of ordering 3 names among 30. Okay, and actually this is 30p3, and which is 30 times 29 times 28. for the first one, for the first person to receive $100, there's 30 possibilities. All names are possible, so there's 30 chances. And what about the second position? Since you already picked one, since you already picked Tom for the first person, uh, you cannot pick Tom again. So 29 names are left for your choice. So the second number is 29. And what about the third one? Since you already picked two names, Tom and Jane, since we already picked two names, you can pick a name from 28 names. So this is the permutation. And 30 times 29 times and 28 is equals this number. Okay, let's move on to example 2.9. Suppose that an assembly operation in a manufacturing plant involves 4 steps, which can be performed in any sequence. If the manufacturer wishes to compare the assembly times for each of the sequences, how many different sequences will be involved in the experiment? Okay, so how many different sequences will be involved? Here, you are ordering these 4 steps. So actually, it's the number of ways of ordering 4 steps among 4. So which is 4p4, and which is 4 times 3 times 2 times 1 equals 24. Okay.